The power of artificial intelligence, in order to understand what AI is and can do, is probably a good start to see what it isn't, since there's so much hype about this topic that is actually a very old part of computer science. So if we think about what AI is not or cannot do, at least not right now. First of all, machines do not understand anything. Machines do not understand anything means that they also cannot reason or deduce by themselves. They need an understanding structure given by people. What machines can do really well is compare incoming data to an existing understanding structure. A lot of bad business decisions are made because people think that a machine would understand something. They think, for example, that a machine that is a good chess player would also be a good analyst or analytical thinker, which it is not. Machines do not understand anything. That means that we as people have to gather the data and the structure and the connections, how the world actually works together. The second thing is that a lot of people these days claim that machines are built after the human brain, which is definitely not true. Just from a numbers game, a large neural network has 1 million to 1.2 million nodes, needs half a nuclear power plant to run. An average human brain has 84 billion nodes, runs on 20 watts, and the brain also has a chemical system which creates infinite combinations or configurations of the 84 billion. And if that's not good enough for you, then there's probably also a quantum mechanical system, meaning that there is entire dimensions missing of what we're doing if we're just configuring neural networks. Why is this important? It's important because it means that consciousness is not going to be created just by rebuilding the electrical system of the brain. The bad thing about this misunderstanding is that we have a lot of discussions about ethical behavior of AI, or what would happen if the machines become super intelligent, more intelligent than people. That is something that might happen in the distant future, but is definitely not out there right now. And the last thing is more about how AI positions itself. It seems that today artificial intelligence is equivalent to machine learning, and the science of AI has done this mistake before, that people who have one algorithm claim to have the solution for everything. That typically led to the problem that this one algorithm cannot solve anything, not everything, and that then the whole system crashes and people believe that AI is just a hoax and so on. This is how we had AI winters and summers in the past. And we should not make that mistake. There are multiple algorithms, and we're going to look at this today. Generally, in the market of artificial intelligence, there's 3 types we have to distinguish. Number 1, we have narrow AIs, meaning AIs that are trained for a particular task, something that does exactly one thing. I often call this as the programmer's answer to McKinsey. What that means is you train an artificial intelligence to behave in a certain way in a certain specialized environment. For example, you train an artificial intelligence to grow tomatoes in a greenhouse. And the artificial intelligence will regulate the water supply, the light, and the fertilizer to increase the yield of tomatoes optimally. That's great, but if you happen to live in England and the tomatoes don't taste that good and you try to replace them with beans, the AI is going to kill all the beans because they just don't turn red. That means you have a narrow AI that is excellent at optimizing this one task, but cannot do any others even if they're very similar. But it's highly optimizing. The other end of the spectrum is what is the science fiction AI. Those are the AIs that we continuously hear about, and I don't like dystopia, so let's make the utopia equivalent of the big AI, science fiction AI, a robot that will go out there and say, I love you, and actually knows what that means and actually means it. Those AIs are simply not available at the moment, and no one knows how to build them. The 40 roughly teams in the world that are working on general AIs have no clue how to build them, and I can be reasonably sure that we won't stumble across that by accident. We don't even know how consciousness works, and before that, we'll probably not find out how to build an AI that behaves like this. If we look at the 3 major techniques of AI, they get combined, and they get combined into what we call general artificial intelligence. And general not in the sense of strong, human-like or anything, but general with general applicability. And in order to understand the general applicability and the power behind that, we have to look at the major concepts that are inside AI. First, If we just use machine learning, we get to narrow AIs, as just described. The natural limitation of this is data. Anybody who builds machine learning systems will tell you that they're working on creating data sets, curating data sets, and then building a model and training the machine on top of those data sets. The challenge is you're using these data sets to explain the world to a machine or give the machine a data set to explore the world. That means if you don't have a data set that describes the now, the world as it is currently, and that you want the machine to make decisions in, then you probably will not get accurate decisions. Let's say you have to take a data set of the last 10 years to describe the soft drink market because you want your AI to make marketing decisions here. That AI is going to make very stupid decisions because it does not know anything about the anti-sugar campaign that is currently running. Meaning, machine learning is fantastic. It can also learn almost anything, but if it has the wrong foundation, not enough data to describe the now, it has a clear limitation where it can be applied. And this limit applies to anything that is out there. Even if you want to train an AI to something that it's really suitable for, like finding cancer on X-rays, the human body also changes. So you probably cannot use a large-scale data set, like a 50-year data set, to actually do this. The second big topic in AI is natural language processing, where we see a lot of chatbots going on there. And the limitation inside these technologies is the simple context. Human language has context. It's not fully descriptive. It's always depending on what is the environment, what is the context, what have you learned before, and so on, of what you're saying. So unless you have a basically scripted dialogue, for example, you have a telephone number where people call in to call sick, and what you want to know back is how long they're going to be out for and when they're going to be back, or if you have a telephone number where you call to make a hairdresser's appointment or an appointment with a restaurant, that dialogue is pre-scripted and there are such and so many ways to do it. That will work just fine in a chatbot. But if you want to see it stumble, try to include something in the I'm calling in sick dialogue that will say, so how does your family deal with it? That opens up so many different contexts. It's simply not doable by a machine currently. Last but not least, we have the old style artificial intelligence, the expert system, the systems that will answer specific questions in a specific area. They typically kick off the old style knowledge management problems, meaning that the benefit you get from an expert system grows linearly with every piece of knowledge that you're adding. And unfortunately, the effort you have to put in to maintain that knowledge base, because it's all has to be fully logical, there can be no contradictions and no overlap, grows exponentially. So the area in which it's economical to run an expert system is actually fairly low. So let's look deeper into the system and then maybe see how we can combine those to form a more general approach. If we have data coming in from several data streams like audio, video, maybe if you are not a person but a self-driving car, LiDAR and radar, then you take this data and you put it in a processor, and the job of the processor is to recognize a pattern in this data and associate a positive action. Sounds too abstract for you? Well, let's put it like this. The pattern is a tiger, and the action you want to associate with that is to go run away. This is what we call the flight instinct, or the fight or flight instinct. That was formed in animals, and it was quite simple because everything that did not have that behavior pattern was eaten by the tiger. We have many of those different trainings, and typically they're all about survival of a species, of a single animal, and the learning is propagated by not being eaten, not dying, not having any adverse effect on your ability to, propagate. And what you have in these systems is simple if this then that rules that get so compressed that at the end of it you really can't explain the if this and that anymore. For example, you cannot explain how to make your heart beat, but you can explain how to add numbers because that's rather new knowledge and the heartbeat is rather old knowledge. So if we look at these systems that are created by iteration and by filtering out the things that don't behave properly in the animal kingdom, we call this instinct building, and in computers, we call this machine learning. That's basically what we do. And in machine learning, unfortunately, we cannot eat things because that's mathematically incorrect. So we found a very complicated mechanism we call backpropagation to simulate the eating part. High-level animals have created something called concepts. And concepts means that if you have associated the the action eat with the pattern herring, and there are many patterns similar to herring, you say, let's associate eat with all of them. So you've now just created the sentence, you can eat fish. Now you only have to learn the exceptions. You can say, we should not eat the Japanese roundfish because that again kills you. Since they're way more edible fish than poisonous fish, you've just outpaced evolution by building that concept fish. The best neural networks today can do some of that conceptualization. Humans actually went much further in doing that. Humans invented language. We are actually able to name everything, all the patterns, all the actions, and just talk to each other. So we don't have to go through this evolutionary cycle of learning by propagation. We can just tell each other. Not everybody needs to have the experience of being hunted by a tiger to actually see if he would run away or be eaten. We can just tell each other to run away. Everyone with children knows that the iteration might not go down to 0, but instead of 70,000 or 100,000, it goes down to 1 or 2, which is also pretty good. With that language, with this ability of language, we've basically outpaced evolution. Language is close to the end of what happens inside evolution, and this is why it is so hard for machines to reproduce. The last step in that is because we now have symbols, we now can name things, we're now able to make an argument. If there is optionality, if there's more than one correct answer, we can pick between, in order to achieve a higher goal, not just simply a goal of survival, but some other goal that we've set ourselves, like investing money to have more money, we can actually set these higher goals, and then we can argue which of the things that we do is the better or the worse to do in a specific situation. That is called reasoning. It can only be done on words in people and on symbols in machines. If people do it loudly, we call this fighting. If we do it quietly, we call it debating. And if you do it internally, you probably call it reasoning. If you look at the algorithms behind this, you'll see that we've now looked at the 4 big pieces of artificial intelligence, where we have the philosophy of the connectionists who think that everything is a network, and that is basically where machine learning is today. Or we look at the philosophy of the symbolists, which is the people that believe in logic and expert systems. This is where you have the reasoning system. And then there's 2 different ways of using statistics, and they're both in the area that is hardest, which is the language part, which is the Bayesian network guys and the analog guys, both with different approaches towards the same thing in statistics. We also have evolutionary algorithms. They certainly can create all of those things, but they are very slow to propagate. Now, the interesting part, if you want a general problem solution or a general solution to something and not just an instinct to react to a certain pattern, or just something that can have a logical argument, but a machine that can have a memory, a machine that can understand concepts, a machine that will make choices depending on these contexts, and so on, you need to build a machine that uses all of those kind of algorithms. And this is exactly what we have done at Arago. We're no longer specialized in one type of algorithm. We've put them together to form a general solution. We're using one engine with one data pool to do all of it. And what does that mean? We use reasoning to actually find a step-by-step problem solution, knowing that knowledge that we've captured from people, potentially, because capturing knowledge from people is way more energy efficient than just watching and trial and error, there might be contradictions, and there might be overlap, and there might be incorrect data and all this. That's what we use machine learning for, to deal with ambiguity in what you're saying, with contradictions, with logical overlap, and with unexpected events. We also use chatbot technology with a predefined dialogue to extract knowledge out of people. And we do remember everything that people have ever explained to us because we want to have that semantic structure to give us context in that area that we've already seen. This is precisely why we are running this general AI solution that can build problem solutions for any kind of vertical anywhere on one engine with one data pool. Now, the difference between what we do and what you find in a normal specialized AI company is very simple. A specialized AI company, for every single problem that they see, they start from 0. They collect the data set, they groom the model, they train the model, and then they can solve the problem that they've set out to do, which is fantastic. And everybody should be using these kinds of AI because they simply do the efficiency models that we have used in our economy for a long time. The difference for general AIs like Hero, like the one we have built, is we can actually build on what we have learned before. So the learning cycle for the next problem is going to be shorter than the learning cycle for the previous problem. And the next is going to be shorter. And the next is going to be shorter because all that data was already in there and because all the knowledge was already in there. So if you really want to go and automate a lot of things, it's probably the only way to do it with this exponential model that constantly reduces the training time, because if the world was standing still, you could eventually achieve a machine that knows everything by solving one problem at a time and training one set of algorithms at a time. But if you know that the world is a changing system, if you know that you have to adapt constantly, there's no way you can actually evolve through this without a general artificial intelligence. And this is exactly what we've built. What does that mean? We've applied it in various areas. We've started out with IT operations. Why? Because we wanted to build an AI that was available to all the businesses out there. We were focusing it for businesses, on businesses from the start. And in order to have that benefit of a general AI that it can learn from something that's already seen and build on that, we had to find a data set that everybody was using. And everybody in business, except for maybe the Irish pub and the Swiss watchmaker, is using IT. So we started in operating IT automatically. And of course, we achieved fantastic sets. We achieved fantastic sets of automation there, 80% automation or even higher automation rates that we see in these kind of systems. But the actually interesting part of this is that we're able to react way more flexibly to change, meaning we put agility back into IT. A change in your primary software no longer means that 6 months from when you started the change, there's still going to be some instability in what you do operationally. That means a change of your fundamental components might now just take a week or so. After we had this data set that is basically applicable throughout the industries, because we've touched it through IT providers, we went to other industries like transportation, maintaining aircraft, taking the aircraft maintenance time down by 50%, or feeding animals, meaning that every animal gets the optimal food to actually get it to where you want it to be by the time it gets invited for dinner. And that in turn means that you can triple the amount of animals you can actually produce at the quality that you want them by the time you want them. Or creating something rather boring like insurances only at 150 times the speed that people can do it opens up entire new areas of where you can build insurances, like for art, which normally is an individual insurance product, and this way a machine can generate it and be there. You see, all these areas are applicable in AI, and all these areas are for us in exactly the same data pool. We handle them with exactly the same engine. There was no additional model building required, no training data required. Actually, what was required was to extract the environmental data from the data that our clients had, and to extract the knowledge of the people who would solve the problems. What we're doing at Arago is we have built a platform that is a general artificial intelligence to automate any kind of process inside business. And we have set out to automate any process in any industry in order to bring massive efficiency effects. So we have more time to build new business models and have more creativity inside these various business models, and not leave creativity and new stuff to the few platform companies that are out there. In order to actually deploy this, we have put together a product and a partner network. If we measure the success of this, we have to look at reach and scale, meaning how many companies can we actually reach today? How many can use our product and how many are using our product? Because those are the ones that will eventually have the efficiencies that we proclaim. And the second one is scale, meaning how fast can we deploy it? how fast can we grow to a useful automation rate, and how fast can we take it from one domain inside the business to another, from one process to the next, from one area of the business to the next, or the next and the next. Those are the things to measure by, because only if there is a large coverage of market will we have an AI that starts understanding the world because people have actually explained it to it, and we have an AI that helps us automate anything in business. It's our goal to make human experience executable, and we only get that if we reach a lot of people with a lot of processes.